Hello everyone, I'm Gülin Yazıcıoğlu and I will present to you our research on minimizing cooling energy demand of an office building with respect to green roof types and the angle of sun shading elements, a case study in Izmir, Turkey. This research paper formed a part of an elective course about performative architecture at Middle East Technical University, together with my colleague Esra, Deniz and our instructor, Assistant Professor Dr. İpek Gürsel, Dino. First of all, I will start with the introduction and then talk about the methodology which we have used, Honeybee plugin of Grasshopper within Rhinoceros, and Energy Plus as our main tools. After that, my colleague Esra Deniz will be presenting our results and discussing what we achieved at the end of the research. Well, when we look at the literature about what affects cooling energy demand of building is divided into two main areas of green roof and sun shading devices. Previous studies compared cooling loads mainly according to the type and static or dynamic features and angles of shading devices as well as green roof types. These studies discuss energy consumption in buildings by separated perspectives such as only implementing shading devices or green roof types. Nonetheless, examining these two issues together would provide better understanding to minimize energy usage in buildings. When we come to our problem statement, nowadays urbanization has been rapidly growing and causes the increased urban heat island effect. Because lack of green areas in cities, urban vegetation has become important role to decrease urban heat island. Therefore, green roofs are one of the sustainable solutions for better environment. Also, it can be seen that sun shading devices provide 35% reduction in total cooling of a building. Therefore, shading elements on facade should be taken into account with green roof as well. As we start our research study, we ask two main questions. First one, what is the optimal green roof types to minimize energy consumption of an office building? And how would cooling load be affected when types of green roofs and different angle sun shading devices are implemented together? Well, as you can see on figure 1, first a typical 6th floor and fully glazed office building is chosen with its surroundings. The building is modeled in Rhinoceros. The building is 18 meters high and has a 300 square meter footprint. Three different types of green roofs, intensive, semi-intensive, and extensive, are considered in order to calculate cooling load of the building in summertime. Also, four different angle sun shading devices are implemented after green roofs. In the perspective of green roof types, the section contains these layers. Only the roof vegetation layer differs in the calculation, as can be seen in Table 1. While making series of analysis, the glazing ratio is set to 90%, while glazing material remains unchanged in all alternatives. And horizontal shading devices are implemented on south side of the facade, which has been exposed by the sun more than other facades during the day. Horizontal sun shading design has only plain 100 cm wide and 150 cm long rectangles. Their angle of rotations are 0, 30, 45, and 60 degree. Right now, I'm handing over the results part to my colleague Esra Deniz.
Hi everyone, I am Esra Deniz. I will continue with the results part. In the results, one of the essential inputs for the calculation is the weather file. We use weather file as EPW format. In this research, EPW dataset of Alsancak is used for the simulation. While investigating energy consumption, the analysis period is defined for 3 months, from the month of June to August. The office building is divided into 6 horizontal zones according to its level. While zone 0 represents the ground floor, Zone 5 shows the 6th floor. In figure 1, perspectives show how cooling load in the building varies with respect to different green roof types and angles of sun shading devices. At the beginning of the analysis, 3 different green roof types are included to obtain average cooling loads for each zone. But exterior shading devices are excluded. Zone 0 has the least cooling load because it's in the ground floor and it's affected by soil temperature. On the other hand, Zone 5 is the most influenced level by changing green roof types. Let's look at the blue vertical rectangle. It frames how the cooling load values differ according to green roof types. As you can see in the figure, upper levels are influenced more. In addition, when we analyze the cooling loads of the green roof types, we can say that intensive green roof implementation is the most effective option, especially for Zone 4 and Zone 5. Secondly, R4 different degrees have been used in the angle of rotation parameter for the exterior shading element. The results show that 0-degree angle shading element has better performance on minimizing cooling load of Zone 5. The red rectangle indicates the minimum kilowatt-hour per square meter. 60-degree angle shading element has the highest cooling energy demand with each green roof types. You can see each combination results between angle rotations and green roof types on figure 4. Lastly, green roof types and angles of shading elements are illustrated in columns. We can compare how implementing 0-degree angle shading elements affect to reduce cooling load in the summer. According to results, using 0-degree angle solar shading on south side of the facade benefits more. Let's look at the results. It benefits more 14.42% for extensive, 14.60% for semi-intensive, and 14.68% for intensive green roof types. To sum up, in this study, types of green roofs and different angle sun shading devices are implemented together. Our aim is to understand better effects on reducing cooling load. The results show that only using one of green roof types is not sufficient as it is combination with shading device on the facade. However, these two different issues are examined as separate subjects in the literature. For further studies, all simulation results about cooling energy demand should be included in cost estimation of the building for the summertime. In addition, the analysis of this study conducted over a single building can be carried out in the urban scale to minimize effect of urban heat islands. This is the end of the presentation. Thank you for kind attention.